job at it.
Okay, I'm now recording, and I should tell everybody who's watching this that this is only slide 2. I forgot to record slide 1. My apologies.
This is slide 1 for anybody interested.
Okay.
And we're not.
Sorry about this. Keep going, please.
Okay. So you write your code in, say, Solidity, you compile it to bytecode, and then the actual bytecode you then deploy on the blockchain as bytecode. And what happens is that once it's deployed, you cannot change the code anymore. It's there forever by design. Nobody's supposed to change the actual code. What changes is the storage of the contract, which I will show you in a little bit later, but you cannot change how the code executes, right? Somebody else might call your code, and because this code essentially will manage valuable assets because you're managing something on cryptocurrency, bugs are very impactful. So, there's actual money connected to it. And if you messed up your code, you can lose a lot of money. And that's why you want to make sure that the code you're deploying is correct, and why you want to do verification. And with this, I'm talking about formal verification, right? And I'm pretty sure all of you have here you have heard about formal verification before. We're doing actual mathematical proofs that the code that we are deploying on blockchain behaves as we expect. We're going to prove properties that hold for all inputs of the program, right? Not as testing, you then predict certain inputs, you're doing it for all inputs. Okay, now I'm preaching to the choir, so I'll stop at this point. But this is how it works on Solidity. And I'm making this point because what I actually want to reason about is the EVM bytecode itself, and I don't want to trust the compiler to the bytecode because the bytecode is the one that will sit on the blockchain at the end. Okay, and now I'll show you when I say ACT, our framework for actually proving stuff about these smart contracts. I mean two things. I mean this entire pipeline that you see here, and I also mean this yellow bubble sitting at the core of this pipeline. Now, why do I mean two things? When I'm talking about this bubble in here, I mean a typed intermediate verification language. So it's like a language where you can specify what your smart contract, what your code does. And then when I say the entire pipeline, I mean verification framework, because what you will write in this language here will be connected on one hand on the left side to the source languages, to the EVM bytecode that you compiled. And on the other side, we will extract this smart contract as a high-level representation in a proof assistant here, okay, on the right side. So ACT, when I talk about this bubble here, not only has a typing system, it also has a well-defined semantics. And we proved, we mechanized actually in Rocq the type safety theorem. So we have a type safe language. And it's what we call source language agnostic because, yes, it works for Solidity, which is the most commonly used language. And I'll show you snippets of the Solidity code in a little bit. But it also works for Vyper. And now we're also working for another language to make sure we can support it. Now, why am I saying this? It all compiles down to EVM bytecode, sure. But if we want to prove what you specify is actually equivalent to what's in the bytecode, you have to take into account little details, which are the storage layout that are defined a little differently depending on which language is your source language. So at the end, we will actually take the bytecode itself as our main input, but we will know from which language you got the bytecode such that we can reason about the bytecode itself. Okay, so what we will do, right? We will, how does it start? You start by having some implementation in a source language of your smart contract. And then what you would do is construct an ACT specification of this language, of this smart contract. And further, once you have this, you will prove that it's equivalent to the bytecode. And this part here, the equivalence part is automated, okay? I will show you in a little bit how exactly we're doing it. But the more interesting part where you can actually prove some properties is the right-hand side of the pipeline, is the proof assistant part. That's the fun part. Here, we actually, here it says we output a high-level representation. It will be a state transition system. And we can prove it in either Rocq or Lean. I will be showing you today lean. Actually, for crypto, it's quite popular. Everybody does lean, 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 but you can do everything you can do in lean also in Rocq. And you can then state your properties and actually prove them. And we will see an example, like a toy example today. And then I will also show you what we did for our case studies, which are a little bit more involved. What kind of fancy properties you can prove about your smart contracts, about your money, right? Actual money. Okay.
Is it actual though?
Wait.
It's crypto money.
It's crypto money. Well,
It's money actually.
can convert that crypto money into actual euros. I mean, my salary is pretty good and I'm getting it in euros. So it comes from the crypto money. That's actual. No? Bought a house yesterday. So that's the money that I got. Okay. All right. Let's look at what's the workflow. I hinted towards it a little bit. So you have, this is sort of like how you would use acts in principle. So you would start here with some contract code implementation already. And then, unfortunately, you have to do this manually. You have to write the specification in this yellow bubble language, right? And this part right here is manual unless you have a very smart cat that can do it for you. In that case, please let me know. I want to adopt her, even though I'm allergic. I would like to have a smart cat.
Could you just give me some idea what kind of things, what kind of specification are you writing? So behavior, desired behavior of your contract, or what?
Not the desired behavior. Desired behavior is the property that you then prove in a proof assistant. It's an intermediate language that will help me generate the state transition system. So for every public function of the smart contract, you will describe how the storage changes. And you will see this in a minute. I will give you a demo and then you will see exactly.
No, but this is helpful. So if you want to prove like, we will never send money to Germany, that's something you do in lean.
Yes.
Okay.
Yes, this is what you do in lean. Yes, it's specified, but the behavior of the contract, you have to sort of have some way to get the higher level representation. Right. And from the bytecode itself, it's very difficult to get the behavior out. Okay. And then once you have your spec written, and I will show you a demo how to do that, then the automated part is when you type check it, because like I said, it has a type system. And then you know that the spec makes sense. And then, essentially by push of a button, you get that your specification is or is not equivalent to the actual EVM bytecode. If it's not, you get a counterexample, you get like input data where it differs. And how do we check for equivalence? I can show you here. What you do is take the bytecode, and then we use a symbolic execution engine. It's called AGVM to get a symbolic representation of the bytecode. So actually it will start with the symbolic state and then execute all possible paths. And you will get like the end state and like the path condition that leads to it. And on the other side, from the act specification, so high level description of what your spec does, you will again do a similar thing, create the same representation, and then use an SMT solver to prove the equivalence, okay? So I don't like that we have an SMT solver here, but if you want to have something by a push of a button, that's essentially what we can do for you at this point. I know that you are formal verification, researchers, so to say, so you care about what's the trusted code base here. So I'll use this slide to show you what is the trusted code base. So yes, you have to trust the SMT solver for now. If you don't, but they're pretty trustworthy. I mean, sometimes more than humans, so it's okay. You have to also trust the AGVM symbolic execution and the symbolic execution of the act spec. It's open source, so you can see what it does. If you find a bug, that's great. But this is the trusted code base. And then what you do is the extraction, right? Once, I will go back to this slide, once you have pushed your button and got like a green flag, it's actually equivalent, and the mathematical reason is given to you by the SMT solver, the automated prover, then you push another button, and then you extract your specification into a proof assistant, right? And then you have like an extraction, for example, in Lean or in Rocq, and then you can state and prove properties again manually, right? Now this manual part, now we live in the world of LLM, so this manual part, like if you write the theorem very, very carefully, you can trust LLMs to do some of the proof search for you. For the simple examples, and if the proofs are uninteresting, I have tried, they prove to be quite, helpful in saving my time to do all of the manual nitty-gritty things. So, if you're actually trying to do it, use LLMs for the proof part, not the theorem stating part. That's a bad idea. They will convince you they're doing the right thing, but they're not. Okay. So this is the equivalence check. And now I want to actually show you a demo of, we will do this workflow for one very simple smart contract. But before I do that for you, because I know that you're not that familiar with Solidity, here's one slide, what you need to know about Solidity to be able to follow this demo, okay? So as I said in the beginning, smart contracts, they are code stored at an address on the blockchain, okay? We have addresses, and these codes, these pieces of software, they manage smart transactions, let's say. So they have some form of like self-executing logic with no trusted intermediary. That's why they are popular, right? Because there is nobody who is governing it. It's like code that executes itself and everybody can call it. And, it's there on an address publicly available for everybody who can look at the blockchain, which is essentially everybody with internet connection. Okay, now they have addresses. So the Ethereum address space is shared between the users, agent accounts. So they're like controlled by the private key. It's like you can imagine a human or like a robot managing, and they want to have some assets in there. Or they have like an address where the actual contract code is stored. So it's like a contract account that is controlled by code. Both of these addresses can have some money allotted to them. You can imagine it, right?
Can you tell by looking at the address whether it's agent or contract?
Yes, because it says, if there is contract code stored in that, then, the content of that address will be the actual code. Or
you look inside too.
Yes, you can look inside what's on that address, and then you see it's a private key or it's a contract. Yes. So you will see the EVM bytecode stored in the address if it's a contract.
I guess I should have asked differently. Do they share the same address space?
Yes.
Okay.
Now a contract, as I said, it's like an object. It will have some storage variables. So they're like typed fields on the blockchain, so they can like manage, they have some sort of internal memory, and they will have public functions. It's like its API, right? How you can interact with the contract. You call its public functions, and then they do something, and you can see the code. What do they actually do? And contracts are then made by calling a constructor. So when you call a constructor, it's run exactly once. At deployment, it was like this deployment phase, and it initializes the storage and like assigns the bytecode to the address. And then you have two, you have other things that I will use in the code further. One is the message sender, and the other one is this transaction origin. So if you want to call a function or something, when you write its code, you can actually get what we call Ethereum environment variables. You can know who is the message sender, so which address is the one that called the public function, right, on the code. And you can also have like the origin of the transaction, so that's the address that originally sent the transaction, that originally called one function, they called another function, they called another function, that is calling the current function. So if your function in your code is being executed, you get access to this data, so you know which address is the one that called the function.
You get just the origin or the entire chain?
You get the first and the last part of the chain, not the entire chain. Yeah. Okay, so now let's have a demo. Let's see how it looks like in practice. This QR code will take you to this last very long link. It will be our running example to follow. Unfortunately, it's not merged into main yet, so it's on another branch. If you want to see it, but I will be showing you hopefully slowly enough so you don't have to. And the other two are our main sort of repository links where you can find the full implementation. It's open source. Play with it if you want. And the other one is the guidebook. It's our documentation, so to say. You have a language reference. You also have a tutorial on how to write your own spec, how to use this thing. If you happen to be super psyched today and want to try it out yourself, feel free to do it. this is the place to start. And actually the one in the tutorial, the one example is like slightly more involved than the one that I'll be showing you today. So that's a good place to jump in if you want. Okay, let's start. The first part of the workflow is to write the spec. And I said we start with Solidity code. So here is like your first script in Solidity. This is all Solidity that I'll be showing you now. And we will walk through it and see what it does. Okay, so I have a toy example. And the idea of this example is that you have a contract which represents some asset that can only be moved by one of the administrators. Okay, so the property that we're thinking is like the only one who can change anything about this asset is one of the administrators. So I will actually have two contracts. One will be the contract that carries the administrators. So it's the admin's contract. It has in its storage, here's how we write it in Solidity. We initialize the storage. It has two public addresses, the admin1 and the admin2. And the constructor will take two addresses as parameters and assign them to the storage variables. So it's a very, very boring contract. It essentially stores two variables, which are the administrators.
So just to understand where this goes, suppose I want to prove that the administrators never change. That's something I will do later in Lean.
Yes.
Okay.
Yes.
Okay. Yeah.
Exactly. So here, as you can see, you can only call the constructor and the actual contract administrators cannot change because we have no public functions.
Right. And it should be easy to prove in Lean that they never change.
Yes.
If that's hard, something is wrong.
Yes.
Yes. Okay.
Yes. Exactly. Okay, and then we will have the more interesting contract, that's the asset contract. And just give me a sec so that I can take a sip. Okay. Now this other contract will have two storage variables again. One is the admins, so we will store who are the admins of our contract. And the other one is a balance of storage variable. And here are the types, right? The admins variable has a type admins with capital A. So it has a contract type, which is the previous contract, the one that you have seen here. And then the second one is what we call a mapping. So it's a mapping from addresses to integers, and it will track which address has how much of our asset, right? It's the balance of each address. Okay, and then the constructor will take just one argument. It will just take the value. And then it will, here in the second line, it will create this balance of storage variable where it will assign all of the value of this asset to the address of this. This is the address of the currently created contract, right? So I am creating with the constructor, I'm creating the contract. I will store it at an address on the blockchain, and I get access. Okay, as soon as I get an address where this is stored, I will take this address and say the balance of this address is the value, and the balance of every other address is by default 0. So nobody else gets anything, just the contract has the whole thing. Okay, and then the admins one, I wanted to make it slightly more interesting. We're not actually assigning the admins at the constructor, but we will choose the message sender, so the one who actually called this constructor, who made this contract, and the transaction origin.
So these are our two.
These are our two administrators,
okay.
Yes. And then to make it more interesting, I will have here a function that can change the administrators. So it's like set admins, which will take two addresses and then assign new administrators, but it can only be done if the message sender is one of the existing administrators, right? So you can change them if you want to assign somebody else, but you have to be one of the existing administrators in order to make this change. Okay, and now the most interesting function is this one, okay? And this one is the asset transfer, right? And as I said, the idea is you can only make a transaction if you're one of the administrators. So here it takes as arguments the amount and the recipient, an address, which is the recipient, and then we will require, so this is like an if the message sender is admin1 or if the message sender is the admin2, so only if you're one of the administrators, then the balance of the contract of this contract is reduced by the amount, and the balance of the recipient is increased by the amount. So this is a slightly boring transfer function because you can only transfer the value from the current contract. You can transfer it to somebody else. You cannot transfer balances between other addresses, but in real world contracts, you could do that, obviously. This is a toy example. We wanted to keep it simple for now.
Can I ask just a small question about solidity? Does it require a return false?
This is an excellent question, actually. This require here will do the following. If the condition is satisfied, it will execute the body of the function. If it's not, it will revert to the transaction.
It will just continue. It doesn't have a body. It'll just say, okay.
Well, this is it will continue, yes. But after this, so if this require is not satisfied, it will revert the entire function. So the transaction will never happen.
So the return true is kind of silly. It could be a unit.
Yes.
Okay.
We don't have a unit.
Yes.
It's a boring language.
Oh, you don't have a unit. But unit is the most boring part. So the other question is, are these functions supposed to be inside the asset contract?
Yeah, they are.
Maybe if we move one of the braces.
Yeah, okay, yes.
Yeah. Okay.
Thank you. Yeah, they're supposed to be in the asset contract. Yes.
Okay, thank you.
Thank you for a very good question. Any other?
Yeah.
Yes, good.
Two more questions.
Yes.
So you said that it's reverted, but is it in fact reverted or is it just not committed until the...
It's reverted. It never happened.
But like if there are things that happen before require, are they actually committed to wherever it's stored?
No.
It's not. So
it's not.
So it's only
entire function or nothing.
Yeah.
Yes. So say that before the require I had some statement that changed the storage, and then I hit the require and it's not, then the entire function.
I'm just wondering where this temporary state that's incrementally being built is held. It's not stored on the blockchain.
No, it's not stored. It's not stored on the blockchain. So the transaction is rejected. It's not part of it. Will never get written in the next block. Exactly.
And another thing, so how do you decide here whether to have these admins as a separate contract or just as a data type inside asset?
You could have just a data type inside asset. Yes. It's a toy example.
Yeah.
Yes. So one of the reasons I did it like this is because then here it's like a slightly more modular, right? You create new admins and la la la. So it can like contribute to modularity. Like the other thing that I'm not mentioning here at all, and so it might be relevant, is that once we are actually executing stuff on blockchain, it costs you a little money to do this, right? It's called gas. Right. And every time you want to invoke a transaction, every time you want to call a public function of a contract, you have to give it a little money so that it actually computes. Right. And then if the transaction reverts, you will not get the money back. Right. The gas that it costs you, it's like gone, it's through thin air. And you want to, make sure that, it might be relevant. How do you decide what's a separate contract or what not? What might be relevant is how much gas it costs you to do the bookkeeping. And on the other hand, what's modular enough that you're comfortable knowing that your code does what you want. So it's
right. So these two fight against each other,
yes.
Right? More modular code is more expensive in general.
Yes, but it's like slightly more expensive.
Yeah, but you quickly get down to optimizing the last percent or 0.1%, and then
yes.
Your boss will say, just write ugly code because it's cheaper.
To be fair, the compilers do quite a good job at optimizing for gas. So they might, write into the bytecode,
yes.
Because the bytecode is the one that actually gets executed at the end. Into the bytecode, they might write it in a way that it's as optimal as they can decide for gas. So they do optimize for gas.
Are they allowed to optimize away contracts, or is that against the specification?
I think that's against specification, yeah. All right. Are we fairly confident that we have an idea of what's going on here? Yes, good. Okay, now let's see how we can take this Solidity code and put it into an act specification. Okay, no, don't read it just yet, the entire thing. I'm now just focusing on the most interesting one, the assets transfer function. And then I will tell you the idea in Act is to sort of describe the end state after the function is executed fully, okay? So every public function, so all of these functions are listed as public. If you have a non-public function, we don't care because nobody else can actually call you. Every public function will become a transition, we call it a transition in Act, and it will take sort of the same arguments as your Solidity code. First thing that we will notice is that in Act here, I have two different case distinctions, okay? One case happens if the argument of the recipient is the same as the address of the current contract where it's stored on blockchain. And the other one is, so one it's where it's the same and the other one is where it's different. And the reason is that the end state, the end storage looks differently in both cases, okay? If they're the same, we are reducing the amount of some address and then we're increasing the amount of the same address. So essentially nothing happens, right? So here it's actually what we call an empty updates block and then it just returns true. In the other case where they're actually different, we have a non-trivial updates block. So for each transition, you will describe how the storage of the contract gets updated, okay? And I only have to mention these storage variables that are actually touched, right? So here I didn't touch the admins, so I didn't say anything about them, but the balance of mapping gets changed. So it's the previous balance of mapping where the address of this contract gets previous balance minus the amount, and the address of the recipient gets previous balance plus the amount. And this only happens when the addresses are different, okay? And then another thing that we have to specify in Act are the preconditions. So it's called an if and only if block, and they are the exact conditions under which the contract will not revert. So I very much appreciate your question about require. When will a contract revert? So one of the possibilities is the one that's written explicitly here in the require block. So if the contract caller or the message sender is one of the admins, so admin 1 or admin 2, but then I have two more conditions here that I didn't have in the Solidity code, okay? And this is because Solidity will explicitly revert anything that overflows or underflows, right? Because these integers are 256, right? So they have a finite range. And then either it would be like modular arithmetic, but actually Solidity inserts an implicit revert into these.
Those are 256-bit integers?
Yes.
They used to be 8 and then they used to be 16. And
Yeah. For us, that we remember. Yeah.
All right. And so we have to explicitly say, right, because we're going to symbolically execute this specification, we have to say, the exact conditions under which this will revert are that the balance of this contract minus the amount will not underflow. So it's in range of this 256-bit integers. And the other one is the overflow. So the balance of plus the amount will also have to be in range. But here we have an implication. It only happens when the address of the contract and the recipient are different, because otherwise you have already reduced the amount here, so the overflow cannot happen, right? Because the previous amount was okay, and then if you increase by the same amount, the overflow will not happen. And if I forget this part here, actually my equivalence check will fail, and it will give me exact like input data where this is the case. So we have to be, and writing the specification, on the one hand, it's painful and looks kind of similar to Solidity, but on the other hand, it really forces you to understand what is going on with your contract, right? You have to understand which are the precise conditions that hold and how the storage at the end will look like.
Can you remind me a little bit about this? The balance of is a dictionary mapping. What is it?
Right, it's a mapping. So it's like a function,
Yes.
Okay, that takes an address and then gives you its balance,
Yes.
right? The actual implementation of Solidity, it will be sort of like a hashed map.
So, but it's a finite map.
No.
No, I mean hash map.
Yeah, actually, it has two.
It's got the functionality of a finite map.
2 to the 256 keys and values.
Yes.
Underline.
Yes.
So you have to.
So you haven't, it is a finite map. It's like, no, I think it's 160 actually.
No, 106 for address. Yeah, for
Yes, because it addresses, yeah.
Yeah,
This particular mapping
but
maps addresses.
Underline.
Yeah.
Key value store of all Ethereum.
Yeah, yeah.
It's this.
It's this. So actually what happens is that it is, you know, for all intents and purposes, only certain keys have a non-zero value, but you don't know which one when you just look at it.
Oh, by default, the others are zero.
Yes.
What if, no, by default, the others have a default value,
Yes.
whatever it is.
Yes.
Okay, yeah.
I thank you for the question. I want to say they're zero for the integers, but they have a default value.
So all types are inhabited.
Yes.
Okay.
It's a simple type system.
Oh. Okay.
Okay. Great. So this is how a transition will look like, right? You will have several cases. For each case, you will specify the update and you will specify the preconditions under which these updates happen. Okay. Then for other things so for the constructors, so actually for every contract, you will have a contract statement in act, and then the constructor will just have a creates block that will do exactly what you would think would happen in the end. So here in the constructor, hypothetically, you could call some other functions of other contracts to compute values. You would actually have to specify them here, what these other functions actually do. You cannot call other functions here, but you can call the constructors.
Why isn't there an if and only if block for constructor? Couldn't the constructor fail?
Yes.
But you don't have to specify this because.
Well, because in this case, it doesn't. Because it's a total.
Okay. So, but in general, there could
Yes,
be
there
act.
could be a require here, and then I would have here, and there could be a constructor.
Yeah, so act supports if and only if on constructors. We're
Yes.
just not seeing one.
Yes.
Okay.
Exactly.
Okay.
You could have it, and then you could, like, each constructor, instead of the updates block, it will have a creates block, and there could be an if and only if. I don't think different cases happen in the constructors. Because it's not an update, but it's like an initialization of the storage. It should be deterministic. Okay. The constructors have a create block, nothing new. And then I have here in red, then you have to specify a transition for every public function. So I omitted the one for set admins. So we can, as a mental exercise, do what the admins one would look like. But also for the ones who know a little bit about Solidity, actually what happens is that implicitly, another implicit thing, here when we have a public storage variable, they will have what we call an implicit view function. Okay, here I say implicit view function, which means it's like just a method that's like a getter function, right? You can read what the storage variable is. And this is like, you don't have to write it as a public function. It's like given to you by Solidity immediately. But actually, you have to specify it as a possible transition in AGD because it is a public function. You're just like getting it for free in Solidity. And because the equivalence check, again, will work from the EVM bytecode onwards, you have to specify all of the possible interface with the contract.
How boilerplatey is this part? Like, does it always look the same in ACT?
Yes.
So it's just something that you could possibly also
automate?
Yeah.
Yes. So having some form of automation for constructing these specifications is one of the things that we're looking into. Like, you could in principle even decompile, but then at the end of the day, you also want this spec to give you some sort of a readable format because you will reason with, the variables that you choose here and and then it's easier if it's like a little bit thought through.
Also, I think the spec shouldn't, if you create the spec from the bytecode, then the spec will say that the bytecode does what the bytecode does, and that may not be the right thing to that's not proper.
I mean, if you can then prove properties about
that's
contracts
true. Yeah.
that you actually desire, it's fine.
Why not just write your contract in ACT? back compiled to you.
Yeah.
I had this question half an hour ago, but I was polite.
Directly
Yes, you can.
byte code,
Yes.
but not skipping.
Yeah.
Solidity.
Yeah.
Version 2.0.
I think you can do this with AI. And then
Yeah.
try to
Then you
check.
just, yeah.
And then
Yes.
literally
Yes,
can
yes, yes.
do a lot.
Exactly. So that's what you can do this. You can have an agent that will do it for you because the equivalence check is automated and it gives you actual feedback. So, I mean, it will be costly because you're symbolically executing everything every time. But in principle, if you just like run it for over a night,
Maybe if you give some optimization prompt, because Solidity it's added value, it's like usual programmable optimization. So it's kind
I mean,
of
but you can,
stuff.
yeah.
You could, agent could do that directly. So.
I mean, you could add, even without agents, you could add hints.
Yeah,
Mhm.
not.
There are other programs that use output apart from my analysis.
Yeah, but the thing is you can then check it against specification.
Yeah, no, sorry, I was just carry on.
Yeah, okay. So do we want to do the mental exercise of
Let's go on.
no? Okay.
I mean, maybe others do, but
Then I want to show you how it looks.
also I'm looking at the clock.
Oh, we can have a break in 3
But
minutes.
it's suitable when you think it's a
Yeah,
good
yeah.
place to stop.
Okay. So here I have it side by side. So this is the full Solidity implementation, and this is the full Act implementation. It's slightly longer, but not too much. And here we have the transition set admins. You know, it again will have the case where the caller is equal to one of the admins. It will actually make an update. And if it's not one of the callers, then it will do nothing. Okay. And then what I can show you now, and it will take about a minute, is that you can error, unable to download something. Okay, let's see.
You seem to be online according to my phone.
Yeah. But I was not online when I typed this up. So
You just will do whatever. How about this? We have a break.
No. I'll give you a break in 1 minute.
Okay.
I want to
So
show.
let's watch live debugging.
Yes. Let's see. Let's see if this is actually working. Okay, so I want to go into the correct directory first, or not. No, I want to say act and then equip. And then I want to give it the Solidity code, which will be in tests, lead admins, admin.sol. And then I want to give it the spec, the act specification, which again will be in tests, lead admin, and admin.act. Yes. So these are the two files that I just showed you here. Up. And then I want to press enter. And let's see if, it's doing something. Okay, it's giving you the success thing. Now for this toy example, it should take about a minute. And if I didn't make a typo, it will tell you it's actually equivalent. So, you know, it is a push of a button. I had to type something. So if you look at what I typed, I said, okay, act, try for equivalence. And then I gave it the Solidity file and the specification. Now I told you, I gave you a whole rant about why we want to do testing on the bytecode itself and not the source file. So what actually we're doing behind the scenes is we compile it to EVM bytecode and then execute the actual bytecode. I give you a pinky promise, that's what happens. The reason I'm giving it the Solidity file is first because it's easier for me because I have the Solidity file there already. Second, because I told you there is slight difference between source languages. So I could do it also with Vyper. This is like the other popular Ethereum language. But the storage layout in the bytecode is slightly different. So we have to take that. So I need just an information, which source language it's from and the actual bytecode.
Approximately how large are the SMT problems that it's solving? Like in some notional largeness, variables, whatever.
Big. Yeah. So they're checking several things, that the end states are equivalent, and then that the input space is equivalent, right? So it's a big, so the path conditions and like the whole thing blows up.
256 bits on the first input.
It's symbolically executed.
Oh, it's symbolically.
Yes. So you don't check the entire 256-bit space. That would be insane.
What is the SMT solver? And can you change it?
Yes, you can change it. I'm currently using Z3. Also, CVC5 is supported. I think in the Nix shell, you already get these two. You can choose whichever SMT solver you want. It exports to SMT-lib. So take your pick. Z3. So currently, Z3 was most successful with our experiments. CVC5 did quite well, except on one, the most involved example, but yeah, they're not deterministic, so it might work for different reasons. Just because the contract code looks like this might be something else. It's worth checking several different ones. Actually, the Bitwuzla SMT solver is very useful for the equivalence check. So it actually uses SMT solvers also for type checking. I will tell you in a little bit why. But for the equivalence check, because there are bit vectors everywhere, Bitwuzla can be, super fast compared to Z3 sometimes. Okay. After the break, we take a look at the proof assistance part.
Okay. So,
well,
let's go on.
All right. Now comes the fun part. We have checked for equivalence. So we did the type checking and the equivalence checking in one go. And now we do the fun part. We extract to a theorem prover. Okay. And okay, this is not the funnest part. The extract to a theorem prover will also be just one command. It will be act clean. I just have to move my Zoom panel. Sorry. So it just be act clean, or you could do act Rocq if you prefer Rocq, and then you give it file. And this is the file to the specification.
And now we see what's up.
Is it visible? Can you see what I'm typing?
Yeah.
It's fast.
Would you like a chair?
No, it's okay. I'm not planning to write much now. Test clean, and then dot act. And then if I do this, it will generate an enormous lean file, and I could save it somewhere, but actually I already have it. So I can just show you. It will be this one. Here.
That lean file generation, it's proof that works correct.
No. What do you mean prove that it works correctly? I haven't proven any properties yet.
Specification to the lean.
Yeah?
That's trusted base.
That's trusted.
All of ACT is trusted. Any output produced by ACT is trusted.
Yes.
Trusted meaning proof or just trusted?
No, you have to trust it. When you say that something is trusted, it means you must trust that thing. Otherwise, you don't know.
But there's a chance that this gets proof.
So let's think about what that would mean.
Okay. So you want the formal soundness proof, right? Yes.
You have to show that ACT works correctly.
Yes.
Yeah. A lot of work.
So what we do, so it is not formally proven sound. We have an almost complete soundness proof. So we did actually prove on paper that what we output here is sound with respect to the ACT semantics, the operational semantic that we have. But then because we're changing everything, we didn't bother formalize it yet. So
it's too early, right?
Yes, it's too early.
What is ACT implemented in?
Haskell.
Because if you implemented it in Lean, that would be a shorter road to having a formal proof.
Yes. So our next iteration, we already started actually doing.
Okay.
Yeah. I can talk about it in the future work section. What happened? Zoom workplace connecting. Am I still on Zoom, Andre? It's like it?
Yeah.
Yes.
But somehow, no?
Now you're not.
I think
Reconnect.
I got disconnected from your hotspot.
Mhm. Might be.
And
And maybe you took the phone with you.
No, I didn't.
maybe it has a.
Are you reconnecting or
I would like to, yes.
are you
I am.
are you
I
on my
just-
phone?
I just clicked on your hotspot. And it's now connecting to your hotspot.
Probably. Let's redo this. So maybe where it says this meeting is being recorded, you can click OK on that. Oh, right. Is that you? Oh, that's the main computer. It's this one.
Yes.
You can just click that OK with this mouse here. And then, okay. Now try to reconnect.
Network connection failed.
Yes.
Let's do it again. Aha. Better. Now I have to go back on Zoom, right? Yeah.
Because I don't see you as one of the participants.
Yes. There it is. This meeting being recorded. Thank God. Okay. But
Okay, I think we're back.
woohoo. Okay. Yeah, so currently we're going to trust the output. Okay, and I will. So here is the full output. Let's not read the entire thing. I will show you first. Where did my slides go? Sorry. I will show you what it's supposed to mean. Okay, so the lean extraction or Rocq extraction, what it does is it takes the act specification and then it will create a state transition system. Okay, so the contract storage, the storage variables will become a state. Okay, will become a state in lean record, essentially. So for this particular example, so for the asset contract, it will have a state where we have 4 fields. These 2 are the actual storage variables, so the admins and the balance of. The balance of will be a function from the address type, which is just, we will model it as just a natural numbers type, into integers, okay?
Actual integers.
Actual integers. That
sounds fishy. Keep going.
Yes. So our act type system proves that this is a sound transition, because the type system itself will check that nothing will overflow or underflow and la la la. You will get as preconditions these conditions if you want to use them in your reasoning, but you get to just use actual mathematical integers in your proofs from that point on.
That's very helpful, actually.
Yes.
Yes.
It really alleviates the proof burden.
Yes.
From you. So you're welcome. We do actual integers, And then the admins will actually take the state of the admin's contract, right? So it will be another record in the record. And then we have 2 additional things. These are present in every state, and they're sort of connected to the smart contract Ethereum environment. So one is you get the address of the contract that was created. It's actually, if you need to reason about it, you get it. And the other thing is the balance, okay? I didn't talk about this yet. So this balance is not this balance of here. They're 2 different things, okay? This balance of here is the internal balance of the contract asset. So it tracks how much of this asset that I just created each address has. This balance here is how much ETH or WAY, the part of ETH you get, and this is relevant if you have a payable contract. You can actually send it actual ETH, the native Ethereum currency, to a contract to any address, essentially. Now our contract was not payable, so this will just be 0 because it's a trivial example. But you could have, for instance, an auction contract, which we tried, and then you would actually play with this balance because you will have payable functions. So
can you just say a couple of words? What does it mean that you have a payable function? What if you want to call it, you have to pay, or what?
Additional to the gas, you always have to pay gas,
yes.
Okay? But that's small amount.
Yes.
Okay. You can additionally pay it ETH. So this is
Yes.
like the native
Yeah.
Ethereum currency.
Yes.
And then you can
But
track
who
this.
pays what? So you pay in order to be able to call, or what? What happens? Who gives money to, who gives ETH to whom?
So every time you call a function, if it's a payable function,
Yes.
you can send it ETH. So it's a special value. It's called call value,
Yes.
right? And you can add it ETH.
Okay.
And then this contract can then use some of that ETH, transfer it to somebody else.
But it gets it.
It
So
gets it. It gets the full
Ethereum
amount.
protocol now transfers this much from you to them.
Yes.
Okay.
Exactly.
So
Yes. And it's not, so it's additional to gas, right? Gas
Yeah.
separately
Yeah,
and this.
yeah.
Sorry, go ahead. Okay, sorry, I didn't follow. Okay, so these are the two extra things. And then the constructor will translate to a predicate describing initial states on this state. And the transitions will translate to the steps between states. So it will be essentially a step relation. And then we also have what we call a reachable predicate or reachability predicate that says a state is reachable if and only if there exists an initial state that can be then, with some steps, we can reach our current state. And at the end, you want to prove properties about all reachable states. So not just any, but the ones that you can actually reach through your contract. You will initialize it first, and then the only way to modify your contract by design is to call one of the public functions, one of the transitions. So the reachable states are the one that are actually happening in the wild, so to say. Okay.
This is all inside the namespace of the contract you're translating, because there's an admin state that I suppose was created from.
Yes. So actually, I will have to first create the admin's contract. So if you look at this, it will first create the admin's contract, and then it will give me the state of the admin's contract, which will have the admin1 and admin2, and additionally balanced address, and then the entire specification, blah, blah, blah. And then, sorry, it will be namespace. And then I have end admins here. Next one is asset, which will use then admins that I just defined here above. Okay, so I have to, for each contract, output the entire state transition. So I do, right? It actually does for each contract, it gives you the entire state transition system.
What's the data type for address here?
I think it's just natural numbers as a simplification. We don't take. So actually it could be if, or no, it's actually uint 160, I think. Yeah. So it's, okay. Right. What do we want to prove about our toy example? The thing that I told you in the beginning, only the admins can change the state. Okay. So my theorem, now I do the manual proof properties thing. Again, if you have a very smart cat that can wait for me, please let me know. The theorem that I want to prove is no admin, no change. Okay. I'm proving here that the state will stay the same if the caller, the message sender, is not one of the admins. So what will be? So it's a theorem that says for every two states and every environment. So this environment is the caller, the origin, and the call value if it would be relevant, but now we don't have a payable one. So this is the balance. I see. Okay.
So I'm thinking whether the environment is the entire Ethereum, but
no.
okay.
We don't need this here. So they're what we call Ethereum environment variables that are accessible when you're writing this. So we only have the caller and the origin of the transaction. So we have the origin, the caller, and the call value, I think. And so it says for every two states, if the state is reachable and if the state prime here is reachable. So if the state prime comes from state via one of the transitions. So this is like a transition predicate, okay, or a step predicate, I could call it step. Then the states are the same if the environment caller is not one of the admins, okay? So I'm hoping that this should be easy to state for anybody who has used Leap before, right? Okay, states stay the same if not one of the admins. And then it's by and about 60 lines of proof that I omitted from the slide. I generated this one manually, but I also then tried with LLMs once I already knew the proof, and then it speeds up the process if you want to, like, if you know what you're doing, right?
The LLMs come up with less than 16 elements.
No, but I was, polluting it because I already knew what I wanted. So, no. But maybe that might be due to my poor use of LLMs, not because the LLMs were stupid. Okay, I can show you the proof actually. Because you are all, fans of lean, I can actually show you the lean proof. Okay, so here it is. No admin, no change. Okay, it's a prime one because I have another one that hides the other things by from an existential quantifier. But this is the one that I showed you. Okay, so for every two states, you have seen this on the slide. And then the proof, I will say this, it's very boring. Okay, essentially what you do is introduce your hypotheses up to here. So I know that my state is reachable. I know that the caller is not admin 1 or admin 2. And I know my hypothesis that the state and state prime are connected via one of the transitions. And now I case split on the transition until I die, essentially. Okay, so I case split on a transition, and then it can either be a transition of the asset contract, or it can be a transition of the admin's contract. And now I'm hoping that you will ask me why and what are transitions of the admin's contract? We didn't have any public functions. Yes, but we had the view functions, okay? And essentially anything could happen, once we're creating this. I know that I have a specification somewhere, but because, and I will show you here a little bit, sorry. Okay, here where I have the constructor of the asset contract, I have another contract in its storage, right? The asset contract here has the admin contract in the storage. So who says that somebody might not call a public function of this admin's contract that I'm storing in my local storage? And this one could also change according to its API, according to its public transitions. So what our state transition system does, it actually takes this into account, that the transitions of our contract can be either internal transitions or external transitions of all of the contract that we're storing in our storage. Okay.
How are the return values going in the state? In the transition?
Yeah, they're not.
They're not. Okay.
No.
Question?
Yes.
How much work does something like grind tactic do here? Have you tried?
No.
So if you do cases H transition and then less than : greater than grind.
Here?
No, after
Here?
cases. I think after the cases here, yeah.
After the case? Here?
No.
No?
Cases H transition and then remove width.
Okay.
Let's do if we're allowed to do a small.
Yeah, sure.
Okay, so now it's less than _ greater than after the cases. Same line, I think it has to be. Sorry, semicolon. It without spaces. This is the tactical that will say
like this?
no.
No.
Space less semicolon
Okay.
greater no space. Type exactly what I say. Okay. Space grind.
Grind failed.
Because you need a tactic. Okay, end of experiment. You need to import something. Let's not do that now.
Okay.
But it's got these hammer tactics that try to do stuff and so on.
Still recognized.
No, grind failed.
No, grind failed. You need to import some tactic.
No, grind didn't finish.
Oh, it didn't finish it.
Yeah.
Oh, grind wants to finish.
We
Okay, yeah, okay.
we have proven the grind. This is actually great case study for grind.
Okay.
Could you try grab?
So you're not talking Rocq instead of lean. So okay, anyhow, but I mean, very likely there are other ways apart from manual work and LLMs. They're in between.
Yes,
things
there are
that
in
you try.
between layers that you can try to
In
automate.
Rocq,
Yes.
in lean,
In
sorry,
lean, yeah.
they're all sorts of tactics that would be good at this kind of case analysis.
Yes. So essentially here we have just a case analysis of scoring. I'm not saying I'm like the best expert in lean. I'm not. But, you know, how the proof looks like, it's actually case split on the transitions, and then it's either asset transfer transition or set admins transition. And let's say it's asset transfer transition, then we again split on the hypothesis and and at some point we will have here in the context either a contradicting hypothesis. One is that the caller, the message sender, is not one of the admins, and or it is one of the admins, and of course that's just a contradiction.
Do you ever do anything, or is it always just case, and then
It's case, and then it's either
either trivial or obviously false?
Yes.
Yeah.
Yes. So it's either a contradiction in the hypothesis, because if we have a transition, we will have a hypothesis that the caller is one of the admins, or it will just be reflexivity because nothing else will actually change the state. So the interesting one is actually here. Yeah. So it's either contradiction or reflexivity, how we conclude this. And then here in transition admins, because you mentioned it before, we have a helper lemma that admin's transition leaves the admin state the same, right? Because what I will have to prove in the end is, but only the admin's field could be changed. And then I'm proving like locally that the admin's state, right, will stay the same. And it's just like reflexivity always, because the view functions don't actually change anything. There are no updates, nothing changes. So it's trivial. So yes, the point of this exercise is that proof is trivial. You could do this yourself. It's not that hard. Okay. Okay.
Well, what's also important, I think, is here that we can understand what you're doing without actually reading and inspecting the generated lean code.
Yes. Yes. You could also inspect it. So our documentation.
But it's quite an important feature, right? Because the generated lean code is likely going to become quite complex for complex things. And then you still want to have a good interface to it that's understandable.
Yes. So the generated output also gives you some help in proving the invariance, the inductive invariance. So we have some like general theorems that we prove for you in generality, and then you can like use them. It's quite well documented in our algorithm if you want to see it, but yeah, essentially describe the states. The initial states will be the constructor states. The transitions will be every possible transition, and then every possible case of every possible transition, right? So here, when we have in this transition, we have the two cases, right? They create a different state in the end. So we will have like every case of every transition will become a separate step in the step relation. Okay.
So
Yes, absolutely.
when the specification changes and you redo the lean code, do you have any mechanism in progress to transfer the old proofs to the new code, or is it manual?
So the state transition system, the names will look kind of the same, right? So for instance, if you added another public function to your Solidity code and another transition to your act code, right? Then you can reuse essentially, but it will give you like missing cases wherever you have this thing. So, but like the names of the existing functions will have the same names in the transitions. So, you know, the outputted.
You sort of generate the new one.
Yeah.
Copy paste the
Yes.
theorems over.
Yes. So actually, what we recommend is to like have a different file for where you're proving things and what you actually output, right? Because this one will be overwritten, and then you just import, and then it will highlight the missing thing.
So regarding your question, I think it's good to be aware of the technique called proof repair by Talia Ringer. I think it was her PhD maybe, but she's worked on it. So proof repair is exactly the methodology and the idea of attacking the problem that Mattia asked about.
Mm-hmm.
When something changes and your proofs don't work anymore, how do you fix them? And so she's worked a bit. I think it's her idea essentially. I think it's from her PhD, but I might be slightly wrong there. But I think it's from her PhD. So that's, if you ever seriously consider this, look up Talia's work.
Thanks
Yeah.
for the reference. That's
We ran into a similar problem. It wasn't spec.
Okay.
Or you can have an LLM with it. Pick one, and
But if you say these things, then Alan will have nothing to say.
Actually merging now with the.
I see it.
Okay, so this was a toy example. Proof was simple. It was, essentially trivial, other contradiction or reflexivity. We have 2 case studies that are slightly more involved and slightly more interesting. So they're like real world contracts that are being used like every day. One is the ERC20 token. So it's a standard fungible token. And the other one is automated market maker, or AMM. So it's, for those who know, simplified form of the Uniswap v2. It's actually a contract that has 2 tokens inside. So it's another example of this multi-contract thing where you have to reason about transitions of the other contract as well, because your internal state can change. Okay. Little bits of statistics. So the bytecode equivalence check, the one with the SMT solvers, takes about 10 minutes for the ERC20 and about 4 hours for the AMM. So, it's stretching its muscles a little bit. The extracted, I'm showing you here Rocq, but for Lean, it's, I think, the same lines of code, plus minus, 10% for syntactic differences. So about 500 for ERC20 and about 1,100 for AMM. But 500 of these is the ERC20 that you see here, because we have to, we actually output all of the nested contracts in one state transition system. So it's 500 plus 600-ish for the AMM. What we proved is the most interesting part, right? So in the ERC20 token, it has a similar thing with this balance of storage variable that you saw in our simplified example. And what we prove is that the sum of all of the balances is equal to the total supply. So we could do a similar thing for our contract, because when we initialized our constructor, we gave it an initial value, right? And then all you could do is like subtract from this value to other things. Now here we can actually have more interesting transactions, but like the total supply of the token either stays the same or it's like, it's tracked in a separate storage variable. And this one is interesting because the space of the addresses, right, is very large, is to the power 160. And because you're reasoning about it symbolically, you never actually execute it, right? You can actually reason about the entire address space on this high level, and you will prove it without actually going through the address space at any point. And the AMM one is like even more important from like a human perspective. So we proved solvency. Okay, what does it mean? The liquidity provider, so in the AMM, you could have some addresses that are investors and they sort of like invest into your contract and like pay something. And then we want to make sure that the contract always has enough tokens that they can exit their position, right? So this is like the solvency property, and we managed to prove it like with this state transition system that the contract will always be solvent. So it's safe, if you play around Uniswap v2, it's safe to invest because you can always get your money back if you want.
So this is exactly the kind of thing that people who want your money would say.
I have a mathematical proof. It's open source. I
can just keep repeating.
Yes. I am not personally invested in Uniswap v2. Okay. This particular contract has nothing to do with my revenue or any of my income. So
doesn't say you know someone.
Yes.
So you have to start wondering why she doesn't have it.
No, you could buy better.
True. I kind of like this one, so it's okay. The proof is not too big for the ERC20. It's like 250 lines of code. That's a short proof. And for the AMM, it's about 1,100. Like, it's a coincidence that the proof and the extracted code are like the same length. But it's like it wasn't too bad. And additionally to these 2 large test case studies, we have like 200 plus specifications to cover the pipeline so that we can actually test all of the language features of ACT and all of the all of the things that we provide for you in the state transition system. So that's it. Okay, now some limitations. Okay, I sold you hopefully the framework. I hope that you will try it, use it, or at least you had fun learning about it. There are certain limitations that come with this. One is, so this is maybe for more specifically to people who have worked with smart contracts, you could have a smart contract that calls what we call unknown code, right? You could call another contract and not have the full specification of that contract, or not even necessarily know the source code of that contract. You could just know the bytecode or something, right? So it's kind of fishy.
Will you always know at least something?
You know which functions you are calling.
At which address?
Yes.
But you don't necessarily have access to the bytecode?
You have access to the byte, yeah, you have access,
Right.
yeah.
Okay.
But not the source code.
Right, I understand
Yes.
that, yes.
So the compilation here would work, but it's not something you want.
It could
Yes,
be
yes,
it could be obfuscated. It could be cryptographically obfuscated. So it gets really hard to tell what it does. Okay.
So we are now currently working on addressing this, like in the state transition system, even if your transition calls some code that might then, about this reentrancy thing, that other thing could call your code again and then could change your internal storage system. Like if you have an inductive invariant and then you prove that your internal transitions will always respect certain inductive property, then you can also assume it if somebody else reentrantly calls you and so on. So we could reason to some extent about contracts, even if they call some weird unknown code.
I mean, this is certainly the kind of thing that is in somebody's PhD on concurrent / distributive something high calculus type things, right? It's got to be.
Yeah.
Sounds like people would have thought about how to deal with these things. Not in this context.
But in another.
different
Yeah.
context,
So we
yeah.
have some prototype already how to do this, but it's not so. This is part of the problem. There are two other limitations that are kind of connected to it. So I will talk about the first one for a little bit. Our work only applies to contracts that don't have any shared references in the local contract storage. Okay. So you can't have a cycle locally. You could have some shared references globally, but not locally. And we actually check this during type checking. So this is why Act, when it does the type checking, it also checks for the no aliasing thing. And it uses SMT solvers to do that. And it also uses SMT solvers to check for preconditions sometimes.
So this helps with your SMT solving, correct? Or what?
Why
is the limitation there?
The no aliasing one is actually a limitation for soundness of the state transition system. Because how I can show you right here, just a little bit. So here, when I have the state of the asset contract, it has the state of the admin's contract inside. And then if this one has another contract, then it has another contract, then it has another contract. And if you have a cycle, every time you would change the state, it could
Well, you wouldn't even be able to define it in lean anymore. It's too recursive.
Yes.
Yes.
So for the soundness of the system, to even do it, we had to have this this limitation in place.
Do we know, do such cycles exist in the wild?
Yes, they do. We have seen a couple of them, but we don't know how widespread they are. But it is one of the limitations. The other limitation is that we cannot support unbounded loops or recursion. This is because of the SMT solvers in the equivalence check. So this is the other thing that we are currently working on. So because the SMT solvers just they will fail, we cannot symbolically explore the entire unbounded loop space. We are now working on how to export at least part of the equivalence proof or the entire equivalence proof to a proof assistant, so you could do it manually in principle. And we would connect this to a deep embedding of the EVM semantics. So the EVM bytecode semantics has like an embedding in Lean, and then we also embed our operational semantics in Lean, and then we can sort of reason about it, that they are equivalent in Lean itself. This also supports partially unknown code, because if we have an embedded EVM semantics in Lean, we can also say that the unknown code will actually execute some EVM bytecode, and we can just use the semantics of the EVM for that particular part. So we can have maybe some more guarantees, maybe not, but like it gives us something tangible to reason about when we call something else, because you do get access to the bytecode. It will then put more work on the manual proof, but you can reason about all the recursion you want there. You get full expressivity, you're not bounded by the SMT solvers. So we were also thinking about doing like a combination, that there are certain, I don't know, sub-problems that the SMT solvers can discharge, and then you will only have to manually prove the parts that the SMT solvers fail on. That's still work in progress.
In practice, people are actually brave enough to pay for execution of unbounded loops.
Actually, you avoid this as much as possible, right?
Yes.
It seems dangerous.
Yes.
Because
Yeah.
it's possible.
It's costly, right? So would people, do you think people would mind much if somebody took out non-termination from?
Actually, auditors always point out that, because you can
No, you can just
spend-
take it out of the language. Like, why is it there? It's because whoever designed the language
Yeah.
grew up on C++ or something.
I mean, there are places like in the Uniswap v3, they have some recursion or unbounded loop or something. But an important thing to say is that, you know, it always terminates because you run out of gas. And we're not reasoning about gas at all.
So it actually, what I'm thinking is this theoretically speaking, this sounds very complicated
The reasoning about unbounded loop.
about loops
Yeah.
and stuff and showing whatever, right? So do you think that the payoff is worth it?
Right. So the thing is, I said everything terminates because you run out of gas, but then reasoning about gas is even more painful. Because it's like complicated how it's computed, and then it gets some like nonlinear expressions and la la la. We could do that, and then you know, in practice, you know, people will just, you know, pay a limited amount of gas as much they are willing to, and then if unbounded loop happens, they'll just revert.
No, what actually no, sorry.
Limiting blocks.
Yeah.
So there is a limit always.
Yeah.
But that's still difficult to reason about. What I had in mind was that if you detect a loop, you just write out, "You're an idiot, I'm calling your auditor."
Or you can build into this that some number
Yeah.
big enough. You
But that doesn't really help reasoning.
Oh, it does.
Yeah, it's kind of nasty. If you have like a random limit of 1 million instead of, hey, is this terminating or not? You now somehow have to use this million in a meaningful way, but it's a meaningless number. It had nothing to do with your source code, and so we need to invent some connection in your proof. It's not so easy.
Might be dangerous even.
No, it's not. It's just kind of useless.
Sure, proof, because this might increase in future, yeah, but
Or have like an upper limit symbolically. The other reason is also we have, for anybody who knows the space a little bit, you may have heard of Certora. This is like, they also have like a formal verification engine, and they basically use SMT solvers to the extent of what they can. And they were interested in using this for their like stuff, for the stuff where SMT solvers break, for like nonlinear problems even, right? Where you could, in principle, like in a proof assistant, you could reason about it manually and it wouldn't be too painful, but for the SMT solvers, it's just like that.
Yeah.
And this is also why we want to partially do the manual equivalence check, because it would enable like complex just expressions where SMT solvers can't reason it
so
over.
how what's the thing there are these guys in Certora according to for compared to what you do?
They have an industrial prover that is much more hyped. Yeah.
Hyped.
Okay.
You got your answer. You got your answer.
No, I mean, they are much more efficient and much more experienced. Yeah. This is like still, it's great. It's very transparent. What they do is not that transparent. So they encode their properties as a verification condition and added to the SMT solver together with the what we call equivalence check, but it's like just a sufficiency check. And so it's under the hood, right? You have like their trusted base, like ours seems big. Theirs is really big, the trusted code base.
We had just talked yesterday with them, and they are really like, yeah, we can do everything.
They can do a lot. They can do a
They're
lot.
really proud. They say they found some bugs that other auditors didn't.
Yes, that's true. But like my point would also be that with ACT, it's kind of difficult. It's not great for bug finding. You will just not be able to complete your proof. Like you could, have a revelation why while you're trying to do it. Yeah, but it's not like there with their SMT solvers, they will just get like, similarly to our equivalence check, they will have feedback. It will say, counterexample. You don't get a counterexample here, right? So they're complementary approaches as far as I'm concerned.
So there's one other option, namely finite model checking, right? Where you're not trying, if you have an unbounded space, you might like potentially your models can be of any size, but you're only able to search for counterexample up to somewhere.
Yeah.
So that's another possibility where you look for a counterexample up to something.
Yeah. But it's again, we have to have some form of automated. So we were actually thinking about, we initially had another SMT backend, like next to the proof assistant, we just like exported to SMT solvers. But that one was just like when we've done our homework and defined the semantics properly and proof type safety, and I would just figure out it wasn't sound. So I had to kill it. But we do have like, one of my colleagues actually is thinking about exporting to constrained whole class automated provers. And there it could maybe also give us an automation, and then we could do like model checking and stuff. Yeah. Now for the last minute, I want to give you a little bit about peek into the future, what we're doing now for ACT. And this is, we will add another verification backend. So it's called Checkmate. So if I just show you here we're extracting to proof assistant. Now orthogonally to this, we want to extract into Checkmate. And this is actually, I'll go back. It's a tool, it's an automated tool to reason about the economic incentives. Okay, so whether or not it pays off to cheat. And what we want to do is actually from the ACT spec that you've already written, then automatically extract to the input of this Checkmate tool, and then it runs on SMT solvers, but it's checking very different things, right? Here you're checking for correctness. So in proof assistant, what I stated was like correct this property, right? Here you actually define which addresses are the players and how much money they get in the end, and whether or not they're incentivized, like economically incentivized to cheat or not. So I gave a talk about Checkmate years ago here at the seminar, if anybody is old enough to remember. And now we're actually trying.
Some people are too old.
And now we're actually trying to make this like an automated pipeline from the spec. So you would actually still have to annotate your spec a little bit to define which addresses you're interested in as potential players. And then their actions, what they can do are actually the transitions of the system. So they can only call public functions. So that's it. But it will it's a nice, I'm very excited about this. So in a few months, it's coming up.
So this one kind of beats the other one because once you know these things, you don't care if the software is correct.
Yes, it's a orthogonal. Yes.
Right.
I mean,
you prove nobody can cheat. I cannot be cheated on. Why do I care if my code is?
Yeah, well, this one sort of assumes certain things, right?
Aha. Okay. Yes. So it might have to assume things about code.
Yes.
Because if you assume nothing about the code, there will be nothing you can prove.
I mean, you assume the spec.
You assume that the function calls do what they're supposed to, which is exactly what you need as a prerequisite.
Yes.
Okay. Too bad. No free lunch.
That's probably like game theory.
Yes.
So you assume rational actors and
No.
Okay.
No.
We're
You-
talking about crypto.
Right. It's game theoretic. It's called game theoretic security. I can give you a little bit. So you're checking for 3 different properties. Okay. They're called weak immunity, collusion resilience, and practicality. Okay, and you're checking for all this. Now, weak immunity will state that you cannot lose assets if you play honestly, no matter what the others do. Okay, so if you go according to the protocol, you will not lose money. Even if the other ones play whatever, they can lose money a lot just to hurt you. You're not gonna get hurt. That's what we check. The other one, the practicality one, is that the rational choice is the honest choice, so the intended choice. Okay, so you will assume that, you know, if anybody behaves whatever, what my rational choice at each point in the protocol is what gives me the best benefit, or like guarantees me the benefit, is the rational one. And the third one is collusion resilience. So basically it checks that if other people collude against me, if they sort of bond together and do weird things, choose interesting, you know, patterns of behavior, they will still get worse off even compared to if they played it according to rules. Okay, so you don't always assume rational players. Like in weak community, you assume you're the honest one, and everybody else plays whatever they want, right? So it's only like assuming rationality and practicality when you check that it's like that the incentives are there, that, you know, if I played rationally, I would choose the honest option.
Do you have any like links or something where you show what you are doing to specify these things in your stable?
For the link between act and checkmate?
No, I mean like documents, resources. I'm interested in driving
for checkmate specifically, I can give you scientific papers with everything. Yes, yes. Just or you can
Also
Google me on my website.
Also your business card.
On my website, we have.
No business cards. Now it's just link.
I think in Japan it might still be business cards. Yes.
I have a personal webpage with all of the publications related to checkmate and link to the repository. So it's open source. You can play with it, but the input to checkmate, right, is not yet automatically generated for smart contracts. You have to do it yourself. We have a domain-specific language that helps you generate these game trees for your protocol, but you can see all of the papers. Yeah.
Another question, because this is also interesting in wider context, not just smart contracts, but in blockchains we have also like this kind of clients.
Yes. Checkmate is developed for more than just smart contracts. Yes, we are now actually, this is like one application that we want to have like a direct pipeline, but you can use Checkmate not just for blockchain. You can use it for anything. You can like reason about tic-tac-toe if you want. Or we have like one example we were considering is like electricity markets that you can check incentives with. It's Checkmate.
Yeah, I'll check your work and I'll come.
Yes, please do. Okay, I think that's it for today.
Okay.
Thanks for sticking till the end.
Thank you for coming and just jumping in.
Yeah, we were able to.
Yes. Niels has a question. Go ahead.
Oh, so thank you for the talk. I have
I don't hear it.
A je tukaj glas, zvok ugasnen. Ne, na Zoomu. Zoom klikneš. Audio je, video je. Niels, we should be able to hear you.
Okay, do you?
Wait, I'll try mine here. So let's see what happens if I do this. Okay, try.
Okay. Am I audible? Or
Okay, go ahead.
okay. Am I audible or?
Yes, we can hear you.
Okay. So I have a question about this, the difficulty with like the large amount of spaces, because what I see that other people might do with these things is that they might use like all kinds of automata minimization techniques where they have some given transition system or whatever, and then they use some kind of algorithms to make it as small as possible by identifying states that are equivalent. Is this something that you also do, or is?
No, we just explore the entire state space.
Mm-hmm. And would such techniques be? Do you think such techniques might be useful to explore in these kind of applications, or?
So you mean if there's like some repetition or yeah,
For instance.
yeah. I don't know, but it could be interesting. Like honestly, I don't know. You can send me a link to if you have any suggestions that we can improve HEVM equivalence check on. That would be really good.
Right.
And
You know
then
which
another,
Niels this was, right?
This is
Yeah.
Anja.
Okay.
yes.
Go ahead. Yeah.
And then another thing that I'm wondering is like you were trusting like the SMT solver for checking the equivalence. Are there any possibilities to make this like certificate based, that rather than just getting a yes or no, you get like an outcome of like here's a reason why they're equivalent or something in that range?
Yes. So if they're not equivalent, you get a counterexample.
Okay.
Yes.
And
I tried it during the break, but maybe it wasn't streamed. I broke my specification a little bit and ran the equivalence check, and then it gave me the input data under which it wasn't equivalent. So you get a counterexample, and it's even faster. So if it's not equivalent, you immediately get one.
so maybe the other thing worth saying here is that now Lean has got built-in support for SMT. No, just for SAT solvers or SMT? Just SAT. Ah, okay, too bad. So have to wait a little bit. Or
CVC5 does some proof export, and they've done some work on importing the certificates.
Okay.
into Lean.
so
So it's able to do some
Yeah.
reasoning with.
What do you mean the
yeah,
alerts?
yeah. And Rocq has a similar functionality. So I think you could try to pump stuff through the proof assistant as well.
Thanks for the questions, Neil.
Yeah, thank you.
Daj tam prżgi nazaj. He's stuck, no?
Yeah, you stuck?
Na zagraj mogę mówić. Okay.
May I ask, how does this SMT complexity grow with the size of the Solidity code? Is it linear, quadratic, or?
I don't know. At least quadratic.
Okay.
Ooh.
Because I think this is the bottleneck right here with the scalability of this thing.
Yeah. But if you want to do a symbolic execution, then there's not much else you can do.
I mean, the plus side is you have to run this once, so even if it runs for 15 hours,
Yes.
you don't care.
But if it fails, then you will want to run it again.
Yes.
Yes, but like for FS, that we have like 20,000 lines of code. I don't know if it would be 15 hours or 15 years.
Safe to say more than 15 years.
Okay.
Yeah, so we were actually thinking whether or not we can make it a bit more modular so that you don't have to check for equivalence, or that you can check for like subsets or like modularly. So
Break it up, right?
break it up a little bit. But currently it's just like one blob. You have to like, when you can break it up if there are like certain functionalities that are independent, right? If they don't reference each other, but anything that references each other has to be present at the same time currently. So it's not great. Yeah. If you have a huge protocol, then it's not great yet.
Okay, thank you.
Okay, any other questions?
Yeah. How expressive is this ACT language? So what kind of numbers do you write in it? Because what we saw here was basically this overflow or this underflow doesn't happen, and that's it. And the rest seem somewhat like boilerplate.
Are you?
Okay. Zdala na zajtem.
Yeah. You don't express properties in ACT. You express them with the full generality of your theorem prover. You express them in Lean. I stated the no change property in Lean.
Right.
But the only thing I am currently specifying in ACT are the preconditions. Yes.
So what kind of things can you express in the preconditions? You have like an implication.
Yes.
What is it? Boolean logic? Or-
Yeah, so it's
You cannot say for every Turing machine there exists.
no, you have things, you have primitives that correspond to what you would have on your smart contract. So you have like arithmetic, you have like multiplication, division, modulo, arithmetic, you have implications, ands, ors, negations.
So there will definitely be Booleans that you can calculate.
Yes.
Decidable properties.
So then, how much of this do you think could be automated? Because I mean, it seemed like a lot of it was, in this case, an underflow or overflow happens, and a lot of this can be
Yes.
automatically detected.
Yes.
So for example, I think in the Solidity compiler, there's like a link to an SMT solver, which actually does try and do that kind of stuff. So you
Yes.
write in unsend code, and it tries to find
Yes.
places where you can get underflows or overflows and stuff like that. So it seems like that part is kind of similar.
Yeah, so there are several approaches. Yeah. So if you wanna, what we want to keep for now is to be language agnostic. Okay. And if you want to do that, then you really rely on the bytecode itself. Another approach that we are also considering, but I'm not promising anything, okay, it's just like what we're considering is now my colleagues at the collective are developing also the core Solidity, the new version of Solidity. And we were thinking about whether or not we can have some integration like directly from the core Solidity, right? So that you would sort of get from core Solidity, compile directly into Act, which you know is equivalent because you can check it and then go on from there. So yes, I think this is a really good idea if it's a language that is used very commonly, like Solidity is, and I'm hoping core Solidity will be too. That would be really cool to like alleviate the burden of writing the spec. Yeah, because now it really looks like you see your Solidity code and then you're like manually repeating everything, right? So yes, if I can do it as a monkey, probably at least LLMs can help me, or we can do some decompilation, some compilation along the compiler into the Act spec.
Right, the issue is, I guess, forgot what your function looked like, where you could
Yes,
overflow.
exactly.
Okay. Another question on the new stuff I had was you proved the ERC20 specification, and in there is like a bunch of arithmetic stuff that also basically is like can underflow or overflow, and how annoying is it to deal with that stuff?
I don't understand the question. Like in the proof itself?
Yes, in the proof. Because you said you in the lean code, you get to work directly with integers.
Yes.
So where is the do-in stuff kind of hidden?
Yeah, okay. I can show you actually. Give me a sec.
You can just also point out that we might get kicked out soon.
Okay. Let's hope not to.
Also, some people might be antsy because they have to go to places, in which case, feel free to run away.
Let me show you a little bit where you can find these things. So, for example, when I'm defining the asset transfer transition, I have a hypothesis called H-cons, and these are the preconditions here that you specify. So these are all of the underflows and overflows and la la la. So actually, you get it as a hypothesis of the transition, the preconditions of the transition. Right?
This is kind of like saying these integers will never be greater than
Yes.
to the
Exactly. So these expressions that I am computing, like balance minus amount for our specific example, will always be between 0 and 2 to the 56. The integer range. But what you get in the end is like the actual integer. So you have a guarantee that it will not overflow this particular expression, and you can have it like, you can use this assumption if you need it, but you also like can just compute with an integer without worrying.
So I think we'll have to wrap up. Thank you so much. But we're not done yet, because we have the last question for you.
Lunch.
Yes. Would you like to walk in the rain to the Hoodburger, or would you like to walk in the rain to the pizza place?
Pizza place.
Okay, good. Hands up for anybody going to pizza. 3, 4, bit schists in an awesome debate. Okay. So meet you downstairs in 10 minutes or so. I'm going to tell them we'll be there at 12:30. I think that gives us enough time. Thank you so much to everybody who's online. Oh, Chris Stone showed up. Or have you been there all the time? Okay.
Malo pogledal.
Piši.